time to listen to Nazareth. State-determined systems. A system, so since we're going to do, dynamic systems and all that stuff, we should probably define it. It's defined as a collection of objects and their relations contained within a boundary. Okay. The collection of those objects that are external to the system and yet interact with it is called the environment. System variables are variables that represent the behavior of the system, both those that are internal to the system and those that are external. That is, with the system's environment. So, let's look at this little illustration of a peanut. Forgot his monocle. Which I don't even remember. Does it go like this? And then...
That would be really weird if it went the other way.
The top hat too.
They're implied. So this is our dynamic system. And inside this boundary, we have the dynamic system. Outside of the boundary, we have the environment. The system interacts with the environment through inputs and outputs. Okay? We're going to consider three important classes of system variable, all typically expressed as vector-valued functions of time t. Conventionally all expressed as column vectors, and called vectors even though they're vector-valued functions, because nothing makes sense and we're all going to die. I don't have any other reason for why. That's the only one I could come up with. So
just put it into MATLAB, see what you get.
What?
Why?
Oh yeah, because the smart engineer said so. Or you guys ever done that?
Because the bald but not excessively bald hamster portrait. So.
When I taught the MATLAB class, I had them take an essay that was, I don't even remember what it was. It was like, oh, I know what it was. It was Sartre's, it was an essay by Sartre. I can't remember which one it was, but it was an existentialist philosophy essay. And I had them process the words in it and then spit out sentence fragments in random order and generate a new paragraph with it. It was pretty fun. You guys are lucky you don't have me for MATLAB.
Thank God.
Oh, man. So consider figure 1.1 for the following definition. So inputs, outputs, system boundary, environment. Input variables are system variables that do not depend on the internal dynamics of the system. For a system with R input variables, the input vector is a vector-valued function, so U. So U is a vector-valued function, so it takes in a real number, it spits back a vector of length R, and we typically consider it to be a column vector of length R, so it's like U1 of t all the way down to UN of t. Or no, not n. R of t. So that is the input vector, so-called input vector. The environment prescribes inputs, making them independent variables. Independent variables being the same independent variables that we've all come to know and love so dearly. Conversely, output variables are system variables of interest to the designer. So that's what their meaning is. So as a designer, we care about these variables, so we make them outputs. For a system with m output variables, the output vector is a vector-valued function y, which is a map from R to Rm, So why we usually do write up t for these things, but I didn't there because I forgot. But we actually suppress it a lot anyways because we don't like to write up t all the time. Ym of t. So yeah. What is this r? What is this one? So in the u and then in this one.
Real.
And the real numbers, what do they represent? What's the physical interpretation of that?
Power.
They take in a real number, these functions, and it tells what the input is at a specific value of time. So that r, it represents time, and then rm represents the vector value. Okay. Outputs may or may not directly interact with the environment. Finally, a minimal set of variables that define the internal state of the system are defined as the state variables. For a system with n state variables, the state vector is a vector valued function. So x of t, you can write is x1 of t to xn of t. So this is that one's pretty vague still. We'll define that one in a lot of detail soon. We consider a very common class of system, those that are state determined, okay? Which are those for which a mathematical description, the state at time t0, called the initial condition, and the input for all time greater than or equal to some initial time t0 are necessary and sufficient conditions to determine x, the state, for all time greater than or equal to the initial time. So not all systems are like this, but every system we've considered thus far is like this, and many engineering systems are like this. The mathematical description of the system requires a set of primitive elements be assigned to represent its internal and external interactions. The equations derive from two key types of mathematical relationships: the input-output behavior of each primitive element and the topology of interconnections among elements. The former generate elemental equations and the latter continuity and compatibility equations. Does anybody want to guess what those will be? That's right. So, we are at an example, and I want you guys to work on this. I'm going to give you guys a few minutes. Actually, got to go grab something. You guys have to do it. I'm just going to leave you guys to it. You guys, just let me know when you're done. No, I'll come back.
No crap. for, are we solving for it? We're supposed to do the input vector and output vector, state vector. I said I'm gonna let you do this.
State vector, what is that?
That's what I'm saying. It's in the thing.
I can print one out today. What's going on?
A system, a system defines a collection of objects in relation to an collection of those. The input vector is VS.
Yeah, input vectors to VS, but
This is what the state vector, I don't know. Elements of equation KVL, KCL.
Hey, Brianna, what's the answer? Nah. Let's go through
Start doing something else.
each one individually. So, oh, by the way, this is totally not the title of this example. If we're going to call it something, we should just call it Ernie. I don't know why. Ernesto. Chavez.
Spam.
So Ernesto Chavez is a professor here
No.
in the English department. Well, political science. Okay. So we have an RC circuit, and so I brought us back to something familiar, right? Something we've been doing. Is it a dynamic system? What do you guys think?
It depends what the input is, right?
Yeah, well, it's
Yeah.
we can say that it depends on what the input
It
is.
is a dynamic circuit because of the capacitors, right?
Yeah, it's dynamic. It's going to change with time. If we change the input with time, it'll change with time. So yeah, dynamic system. We can define the system boundary kind of however we want, but I think that for this circuit, there's a pretty natural choice for what the system is and where the boundary is. Okay, so let's make that choice. So we don't want to include this source in the system because the source we want to be able to specify independently of the system, right? So the source should be outside the boundary. The resistor and the capacitor, though, they should be inside the boundary because they're part of how the system works, how it responds. But V out is going to be outside, right? Because it's an output. So we'll leave those terminals sticking out to sort of give us that idea. Yeah?
Why does it come out? I mean, the source of it?
Why did we leave it out? If it's an independent source, then we want to leave it out because we specify VS independently of the system. So VS is whatever it is, no matter what is happening inside this circuit. That's how we've defined sources so far. A voltage source is going to be something that is independently specified. Now, there are dependent sources. We've seen those a little bit. And a dependent source would be included. And that's because it might depend on like a current or a voltage inside the circuit. So if it's dependent, we can include it inside. If it's independent, we should leave it out, which most of them are independent. So good. So that's a boundary. That's pretty good. So our VS we're going to consider to be an input here, and then this V out we consider that to be an output. We can choose our output. We could have chosen our output to be multiple things, but we chose our output to be the voltage across that capacitor. Okay, so this was like step one, or not step one, question one. Question 2, the input vector. What do you guys think?
BS.
Yes.
So VS is definitely an input variable, and it is our only input variable, right? So our input vector we always write with a U. So U of t is equal to, it's going to be an R by 1 vector, right? Column vector. R is the number of inputs, so we only have one input. So that's just a 1 by 1. And the variable is Vs of t, as you guys said. So that one's pretty easy. What about the output vector?
BL.
Be out.
The out, right? So just y of t equals, it's an m by 1 vector. In this case, v out is the only output. But we could have chosen, so for instance, we might have said, oh, okay, v out, but then also
BC.
IR, maybe we care about what IR is. So we could have then written v out and IR. And that would have been totally valid.
But you
Why
you,
AR?
you couldn't have done that with the input vector.
Could have done that with the input vector as well. So, but we would have to draw another source. There could have been like a current source too, right? And then if that was IS, we could do VSIS as our input vector. So we could do that too. These are just like, these are not true for this problem, but these could be true.
Why the current for resistor and not capacitor?
That was just an arbitrary choice.
Okay.
It was a choice saying, okay, maybe I care about what the current is to the resistor. Maybe
Gotcha.
for some reason
Any
it's interesting to me. We met once and just like to keep tabs on it. A state vector is a little tough for you guys to do because I haven't really told you how to find state variables, but it's a minimal set of variables that describes the dynamics of the system. And you might not be surprised to learn that the order of the differential equation required to describe the dynamics of the system is the same as the number of state variables that you need. So, if you have a first order system, you need one state variable. If you have a second order system, you need two state variables, etc. So, in this case, do you guys remember? I mean,
First order?
it was a first order system, right? We'll learn more about how to decide that. But
Only because we've done this so many times.
we need one state variable then. And actually, it's not a unique choice. So there are many choices. We're going to develop a sort of convention for choosing state variables in this class. And we haven't learned that yet. Technically, you could choose really any of the variables in this circuit, including like their derivatives and integrals and all that stuff. But we're going to choose one that we'll end up choosing later, which is the voltage across the capacitor. That's going to be our state vector. It's just need one in this case. So I say an elemental equation. Let's write two elemental equations because there are two elements. So what's the elemental equation for the resistor?
VR IR times R.
And what about for the capacitor?
DC dt. 1 over C times RC.
Good. So those are the two elemental equations, same as the elemental equations we developed previously. So a lot of this is going to just be, I mean, it's intentionally an analog to the electronic stuff that we're doing. So it's not going to end up being surprising. And then 6, and which equations might be continuity and compatibility equations? We haven't really defined what compatibility and continuity equations are, other than to say that they deal with the interconnections and the topology of the of the system. And so we heard some folks that were saying maybe this is KCL and KVL. Do you guys buy that? No?
Maybe, yeah.
So if I was like, here's a node, and I said, what is KCL there? You'd be like, oh, it's IR equals IC, right?
True.
That is an expression of how these things are connected, right? It's saying the resistor and the capacitor are connected in series. They share a current. Similar with KVL, if we go around a loop, we say this voltage plus that voltage equals 0. Another way of interpreting that is saying, oh, this is a loop. So KCL and KVL are special types of continuity and compatibility equations. And in fact, there will be analogous versions of that for mechanical systems as well. So, but we won't call them KCL and KVL, we'll call them continuity and compatibility equations because Kirchhoff didn't think about mechanical systems. Unluckily for him, missed the boat on that, but of course we wouldn't have thought of doing it unless he had done it for electronic systems, so, give him a little credit. So, it's KCL and KVL. Oh man, did you guys see that? That was a nonchalant ampersand right there that just happened. No, nonchalant, that's not an ampersand. Is it? Yes, ampersand. Nonchalant ampersand, which would be a good band name.
Looks like a tree.
I like it.
Do you listen to podcasts?
Sometimes.
Stuff you should know. Have you listened to that before?
Once.
Did you enjoy it?
I can't. I feel like. Is this like some guys who like sit around and talk about something?
Yeah, they'll just like.
Yeah, pretty in-depth about it.
Okay, wait, let me rephrase. So, I think I might have listened to one, but I think it was a bad choice. I listened to one on horoscopes or something, and so as someone who's like not into like horoscopes and stuff personally, I was just curious to learn about it because a lot of people in this area are really into them. And so I was like, that's cool. Like I didn't know that was a thing that people like to do for actuals. So I was curious to learn more. So I thought, I'll listen to this podcast about it and I'll learn something. But it felt like some guys who like got on the internet for like a couple hours and read some stuff about it and then just got on and just like shat all over it for an hour. And I was like, you guys, this is like, it doesn't feel like you guys really are like, this is not a great way to learn about this. Like, maybe not like from like a true believer either, but like at least somebody who's like, like people really believe in this and whatever. But no, they're just like making fun of it the whole time.
I think their technical ones are a lot better. Or they just explain how like, I don't know, a water pump works or something.
Yeah, maybe I should have started something like that. And maybe, I don't know, maybe I wasn't being fair to them. I would probably have a hard time not doing that too. I probably just wouldn't pick that topic because that's probably what I would do too. Not that, I don't know. I know some people who actually find value in it, and so that really made me question my maybe lack of sensitivity to how they experience it. So, but I feel like these guys lacked all sensitivity to it. They were just like, people believe this? Which is like, you can say that about a lot of stuff. And I do. Anyhow, before we start talking about things that I really shouldn't start talking about, like religion, I am going to move on to the end of this lecture. Here we are. Are there any questions?
About
Horoscopes? I have lots, in fact. About these definitions, these systems.
So
Why do we only choose one state vector if we have two?
I was just gonna ask
So we needed a minimal set of variables. And so the minimal set for a first order system we'll learn is 1. And so we can only choose one variable. There obviously are second, third, fourth order systems, and then you'll choose more. But it is not the number of elements. It's approximately the number of energy storage elements. So number of capacitors and inductors in your circuit, for instance, but they're not always independent, in which case they don't give you an extra state variable. So we'll talk more about that though. Any other questions? Pizza at the party, the ASME party today. Don't forget. ASME party. Don't stop.